Hey everybody, this is the second segment of the Igneous rock chapter. I had to go back to the differentiation because I realized that I have had some stuff I wanted to tell you. Um, as I already kind of mentioned in the first segment, there are about 200 different igneous rocks, which is a whole lot. So scientists have been wondering, how do we have that many? What has happened? Like, do we have different magmas forming, or we have the same magma and the different igneous rocks are forming by the so-called differentiation? When you think of differentiation, I kind of want you to think of like leaving a milk, a jar of milk on the table while you're on vacation. And when you come back, like a week or 2 weeks later, you look at your milk jug and you see, what do you see? You got the butter on top, then you have the sour cream, and then you have that liquid on the bottom. It's pretty nasty though. But what do you think about the liquid? How about the composition of that liquid relative to the original milk? Has it changed? Yes, it has, because you left it for 2 weeks and the butter and the sour cream has separated out of it. This is what we call differentiation. When the magma crystallizing, at the beginning, some minerals are separating out of the liquid, the magma. So therefore, the leftover magma's composition is changing as the minerals are coming out of it. So this is what we call differentiation. And so this was the idea of this scientist, as I already kind of mentioned. His name is Bounds. Actually, his name is, oh, I didn't write it down. I don't know it out of my head, you know. I just know that his name is Bounds. And he is a geophysicist, but he was really interested in igneous rocks. So he set up a lab with some small furnaces, as you can see here. And he put all the igneous rocks he could collect, which was all 200 different kinds, put them in the furnace and warmed them up, heated them up. And what he realized that by about 1,200 degrees Celsius, everything was molten. So every solid igneous rock melts around 12, like at least by 1,200 degrees Celsius. So 1,200 degrees Celsius, everything was molten. So when everything was molten, then he had this precise temperature gadgets, so he could cool down the furnaces really extremely slowly. And there was a microscope inserted into the molten the chamber of the furnace. So while it was cooling down really slowly, he could actually see what was happening in the furnace. And it was amazing what he came up with. He came up with that any time he ran his experiment, the minerals were crystallizing in the exact same order, which is kind of amazing. Nobody knew it before. So the minerals were crystallizing in the same order, and he had done his experiment a whole lot of times, and he come up with the so-called Bounds reaction series. Bounds, I mean, he didn't name it after himself, but he come up with this reaction series, which actually describes the wave of the magma's cooling, which is very, very interesting. So on this slide, you can see the Bounds reaction series right here. And of course, you will have to know this. That's without the question. It's going to be on the second test and on the midterm. So you really, really have to memorize this. And it's very interesting. If you understand the Bounds reaction series, you understand everything about igneous rocks. So I sometimes do call it the Bible of the igneous rocks. You know your rocks, your composition, your mineral composition, everything. So he realized that the minerals are crystallizing along two branches, especially at the higher temperature. This branch here is what he calls the discontinuous branch. In this case, the minerals crystallizing stop, and new mineral starts crystallizing. So this is kind of broken up. That's why he called it discontinuous. On the other side, which he calls the continuous branch, the minerals don't stop crystallizing, they just get bigger and bigger and bigger. Like here in the middle is the core of the mineral, and then it grows in zones. And difference between the zones, that in the middle it's mostly calcium rich, and at the edge it's going to be mostly sodium rich. So on this side it's all plagioclase minerals with calcium rich at the beginning, and as it gets cooler and cooler, it gets more and more sodium rich. So that's the bounce reaction series. And the very last mineral around 800 degrees is going to be the quartz. So I actually am going to draw it for you, however good I can with you know, I'm drawing with a mouse. I wish I could somehow change it to a pen, but I can't. So here we are. I'm going to try to draw it to you. It's very important that you'll know it too. First of all, we have to know the SiO2 content. And the SiO2 content is going from about 35% to about 65. So that's the SiO2%. It goes from 35% to about 65%. Now the temperature, I'll put it on the other side. Temperature, oops, I drew myself. I pulled it through myself, but that's okay. I'm still here. I'm good. So the temperature in degrees Celsius goes from 1200 to about 800 down here. Oops, I'm drawing on myself. Degrees Celsius. Okay, so the two branches, remember this one, and I'm not going to write it down because that would be a killer for me, is the discontinuous. The other one is the continuous branch. And on the discontinuous branch at 1200 degrees Celsius, the first mineral which starts to come out is olivine. Olivine. Now remember, what is the olivine? Yes, olivine is an iron magnesium silicate with isolated silicate structure in it. So it's going to be just the tetrahedron, silica oxygen tetrahedrons. When olivine finishes to crystallize, it sometimes even dissolves a little bit back, but then the next mineral comes out, which I hope you would know, because it's also an iron magnesium silicate with chain silicate structure in it, and that's going to be the pyroxene. So pyroxene is the next one. Remember, it's an iron magnesium silicate with chain silicate structure. So now you would know which one is going to be the next one on this branch. Yes, it's the amphibole. I'm just saying amphi, but it's amphibole. And then the very last one is going to be biotite. And if you remember, the biotite is a sheet silicate, iron magnesium rich sheet silicate. Amphibole is iron magnesium rich double chain silicate. So as we go down, the silicate structure becoming more and more complicated. So that's very important to know that the silicate structure becomes more and more complicated, and actually these silicate structures are moving around in the magma. So it's gonna make the magma moving slower or faster depending on what kind of silicate structures are in it. Okay, on the other side at 1200, the first mineral which precipitates is gonna be or crystallizes calcium plagioclase. Remember, this is the continuous branch. Continuous branch. Continuous branch, remember. So it's calcium plagioclase. I don't think I will be able to write the whole thing, but it's calcium plagioclase. I just put that much. And remember, it doesn't stop crystallizing, but by the time it gets to about 1000 degrees, it's going to be sodium rich. So it's a Na plagioclase. plagioclase. Okay, so remember, if you look at the feldspars, remember the plagioclase is also feldspar. We just went through the mineral chapter. So as it grows, the composition is changing from calcium rich towards sodium rich. So calcium in the middle and sodium at the edges. So you remember that. And this is plagioclase. Plagioclase, remember, is a group name for feldspars, or their group name is feldspar. Okay, when we got to about 1000 degrees Celsius, you have to understand that all the iron and magnesium which has been in the magma has been crystallized, because these guys are all iron magnesium rich silicate. On the other hand, all the calcium and sodium has been coming out from the magma too. So the magma, the leftover magma, doesn't have more iron, magnesium, calcium, or sodium. So all what we have left in the magma is the potassium. So down here it's going to be potassium feldspar. Remember K feldspar, but it's also called orthoclase. So remember, that's a synonym for K feldspar. So it's K feldspar. Now, if the magma had any water, there will be some muscovite right here. Muscovite. And as I already mentioned, the very last mineral which will crystallize is when no any kind of cations are left. The very last, which only contains silica and oxygen. What is that going to be? Of course, the quartz. I already kind of told you that, so you should know. Now, this really defines the different igneous rocks, and I will come back and put that on. But before that, I'm going to go through the next slide. So Barnes thought that this is the way all the igneous rocks form. We already know that this is not really the way every igneous rock form, but it was nonetheless an explanation of what might have happened. So we do know that it doesn't really explain all the igneous rocks we know today, but I personally have seen differentiation in a lot of places. I traveled around. Even in Hungary, we have magma which starts in one kind of rock and then ends up in a different kind of rock. So there is differentiation, but it definitely cannot explain all the different types of igneous rocks we found on Earth. So the bounce reaction series is really good for explaining the type of magmas, the type of igneous rocks, their temperature, and then their silicate content. So obviously we are gonna talk about the different types of magmas, and it's really, really important for you to know that we have 4 major different types of magmas. The first one is the ultramafic. When you have an ultramafic magma, the SiO2 content is less than 35%. You got to know these percentages, so it's important to know. The next group is the mafic. They have 35 to 45% SiO2. Remember, all these minerals are silicate minerals, so they have silica and oxygen in different structural forms. Like, remember the isolated, the chain silicate, the double chain, the sheet, and the framework. And on the bounce reaction series, all of these are represented. So every mineral on the bounce reaction series and in the igneous rocks are silicate minerals. So they all contain silica and oxygen. And therefore, it's logical that we can classify the igneous rocks based on how much silica and oxygen are in there. But, in that case, we're not calculating quartz content, but the silicate. Every mineral has silica and oxygen, not only the quartz. So remember, that's what we do here. And the next group is the intermediate, and that is between 45 to 60% SiO2. And then the felsic. The felsic is more than 60% SiO2. So if I go back to this figure now here, or the one I just drew, which disappeared. So this one, if you have an igneous rock with only just pyroxene and olivine and pyroxene, we call it ultramafic. I put right here. Okay, so ultramafic. It might have been written, might have been written here. If you have calcium plagioclase, olivine and pyroxene, it's the mafic. And if you have amphibole, biotite, and mostly sodium plagioclase, it's the intermediate. And if you have those plus K-feldspar and quartz, that's the felsic. And so it's very important, if you understand this classification, then you exactly know what kind of minerals are in what kind of igneous rock. See, if you learn the bounce reaction series with the minerals on it, and you learn the group names and everything, you're good to go. So it's okay if you just memorize this right here, this table. You don't have to do the one I just did, but either way, it's good. So as you see, basically, this will explain every igneous rocks, but it does not explain how the different magmas forming. So now that we went through the different magma types, before we go where the magmas form, we still have to understand the so-called partial or fractional melting. But before I get into that, I guess I have to stop because I am at 16 minutes, so I better stop and start a new segment. So I'll see you for now. Bye.